Hello guys, so we again here to discuss the sample problem of real-time analysis using the virtual concept and virtual. So the problem is a simple problem about a triangular slab with simple supported edges. Shown here on your screen. Basically, the dimensions are given to be built into one supporting side, right angle with the edge here, and the distance is 16 feet, as shown for the space and the height of the triangle stone. So the moment X and MLY are given to be square foot and 10 square foot. So I'd just like to remind you guys that we will subscript X and Y in this particular notation. So up until be an indication that this is actually along, not above the axis. It is directed along the x-axis. So this is built from the reinforcement data to the basis for your moment capacity for the portion also thickness slab. So for the procedure build to prove, all we need to have is an arbitrary midline given with the location here defined to be x. Actually, you can assume exactly a point upon which the build line will actually be directed. As we've shown in our previous discussion, that there will only be a slight difference between doing that in terms of the value of your nuclear capacity. Although of course here in this particular example we need to be exact as we are to determine the value of your x that by which that will be ultimately minimum. We are using an optimization procedure here for us make use of uh, multiple. Okay, so for your geometry, we take note the center of your two step segment, which is segment number 1 and segment number 2, will always be located at 1/3 the height of a triangle, whatever triangle this is, and it will actually be crossing or the median will actually be crossing this point of center of gravity. So this line here is the median that is going from the vertex to the midpoint of the other side. Okay, so we divide b minus x by 2, so we can find 1 prime there and x over 2 prime. Wherein this will be the basis now for your virtual uh, displacement. Okay, the virtual displacement here, which is 1/2 of whatever is your actual displacement at this point. So if the displacement is 1, then this is just at the midpoint, this is 1/2 of your delta, which is 1. Okay? But since this is not located at the edge, we have to project it also at a point where this is at one third of your height. Therefore, your delta prime I and actual delta I will still be two-thirds of what your delta prime I is. So if this is one half and that is one half, then your delta I, your virtual displacement exactly at these points 1 and 2, you simply will be one half of your two-thirds delta I prime, which is one. Okay, this is one delta I prime. Okay, so if your delta I prime is uh, 1, then simply this will become 1. Of course, this sum into IH. That's why you still need to multiply it later by H. Okay? So, for the virtual work method, we know that to obtain a minimum amount of energy work done, we have to equate the external work and the internal work to be equal. Okay, so your external work will be done. This will be done by loads, load ability, and your internal work will be done by the internal moments. Okay, so your internal work will be done by your internal forces. Okay, so first we get the external work, and we know that the external work is simply force times displacement. So this Wi here constitute the two segments of slab. So we have two segments, okay, W1 and W2. Okay, so we have two segments deflecting or having a displacement of delta 1 and delta 2. So whatever is the weight of the slab, which is simply the area of the slab, one half the area is base times height, okay, times portion ultimate load multiplied by, so this pertains now to your area multiplied by load multiplied by shear delta. Okay, and this is now the area of the other segment. Area multiplied by delta. Okay, okay, one third depth was obtained down to this one. Okay, okay, so manipulating this equation here, we get now a simple W1 over 6 pH W X will be cancelled out. Not always, but sometimes this happens that your external work will no longer be in terms of your unknown parameter dependent. Okay, for the internal work, we have to compute this on the basis of the number of field lines. So the number of field lines here will constitute the J parameter. So the J simply refers to your yield lines. Okay, number of field lines are actually uh, is only actually one. There's only one yield line here because we don't expect a yield line on the supports because these are real, real axis rotation. Okay, so these two here and this one here are axis. So this is now only have one yield line. Okay, so we only have to worry about one uh, product term here, M and B1, L1, alpha 1, where L1 is the length. Okay, so this is the length. Okay, alpha is the rotation, and M and B is simply the moment. Okay, so the moment multiplied the length will constitute a kick foot per foot times foot, so this would be meters. Okay, and in our previous discussion, I have derived to you what is the formula of your bending moment in terms of the reinforcement capacity. So this is the moment capacity provided by the force and strength of your slab because of its inertia and reinforcement. So the equation is simply mx sine squared theta plus mx plus sine squared theta. So we simply substitute your x to be 8 here and your y to be uh, mnx. Sorry, this must be m and y, and this must be m and x. So this must be 8 and this is okay. So there's some errors here. So your length is simply h squared. This is simply um, your height is simply 12 squared plus x squared. So x is in, and alpha 1, the rotation has to be solved in terms of the actual geometry of the figure. So the geometry of your figure states that this will rotate. This is your axis of rotation, the yield line. And therefore, if I cut a perpendicular line here, I can be able to draw the rotation in terms of this parallel to this line. So that this is your deflection 1. My rotation at this point will simply be equal to alpha 1, which is theta 1 plus theta 2. Remember that this is a real axis of rotation. We are going to have to worry about this. No? I'll show you. This is not a yield line. Only have to consider the rotation at the yield lines. No, not at the rotation at the real axis of rotation. Okay, so this alpha 1, theta 1 plus theta 2. And we know that theta is simply the arc tangent 1 over this distance. So this is the square root of h squared plus x squared. The tangent of uh, psi. Psi is exactly this one. And this is your phi here. Okay, which is theta 2. So theta 2 is simply the arc tangent of 1 over x over h squared h squared plus x squared. Okay, so this is quite very involved. So, but still, alpha 1 can be solved in this particular equation. So m and d1 is now 8 cosine squared phi plus 10 sine squared phi. Okay, so based on this formula here, 8 sine plus 10 cosine. And if we substitute Okay, if we substitute this, I think there's an error again here. I'm not correct. This is supposed to be 10 and it must be 8. Okay, this is supposed to be 10, this is supposed to be 10. Okay, okay. So my internal work then will now be equivalent to MND1 times L1 multiplied by alpha 1. Of course, your L1, as was indicated here, has to be multiplied. Okay? What happens is that your L1 h squared of h squared plus x squared here will actually cancel out with, with this one. Okay, so if this value here is the reciprocal of okay, so they will cancel out each other. That's why this will not be equation. Okay, differentiating with respect to phi, or okay, I don't want to use, I don't want to make my variable phi as my primary parameter. I will now convert phi into an x, okay, later, or I can actually directly use phi here if I'm comfortable using phi as my independent variable. So it doesn't matter what variable are you differentiating the work, you know, to make it optimal, because you are minimizing the internal work done to get in ultimately capacity, the minimum ultimate capacity that is needed, that will uh, minimize the energy within the system, within the virtual world system. Okay, and upon differentiating and equating it to zero, unfortunately, this is very difficult to solve analytically. We use numerical solution to come up with an answer for your p, which is in between this case 0 and arc down over p of h. So this is now 53.30 meters. Okay, so if this is 53.13 degrees, then we let the system solve itself by adjusting. It's an iterative solution procedure that will converge to a final value of your p equivalent to 25.5. So this 25 is in between 0 and 53. Okay, so it's final value. And knowing phi, we can solve for the internal work, which is 34.126, and equating it to the external work, we yield this result for your ultimate work. So I'd like to check this value later using another method, which is the equilibrium method. So this I will discuss to you in my next video. Thank you very much for listening. Have a nice day.